Hello, and welcome back to your online professional development. I'm Stephen Smith. Let me give a big hola to our friends in Puerto Rico. I apologize that I don't do more of these in Spanish, but the limits of my Spanish ability, basically I can tell you I need to use the restroom, I can ask for another beer, and I can string a litany of horrible words. Most of them I don't know what they mean, but I know they're all bad. So I figured maybe that's not appropriate for this video. Instead, we're going to talk about microgravity concepts. I'm going to give you some vocabulary that you'll hear as you're on site here and talking about microgravity. So I guess the first thing to do is we're talking about the Microgravity University for Educator is for us to talk about what microgravity in fact is. So microgravity is the condition in which people or objects, and I'm going to use this word very specifically, appear to be weightless. This is in fact not zero G. Zero gravity is the thing that doesn't really exist in nature because everything has mass, everything has gravity. And even if you're way out in space, think about how far Neptune is away from the sun, for example, and yet there's enough gravity pulling on Neptune to keep it in orbit around the sun. So if we're only, for example, 250 miles away from the planet, we are not in zero G. We're actually at about 90% of the gravity that we would experience here on Earth, but we are in a condition of free fall. So the International Space Station is falling around the planet. So one of my favorite writers, Douglas Adams, who wrote The Hitchhiker's Guide to the Galaxy, he explained flying in his book as throwing yourself at the ground and missing. Well, that's in fact what we're doing with the International Space Station. The International Space Station is falling towards the ground, but continually missing. So we're falling, and the things on the International Space Station are falling at the same speed, and therefore they appear to be weightless to people on the space station. Zero gravity, technically, by the way, just in case you want to totally geek out here, is actually 1 × 10⁻⁶ gravity. There's no such thing as zero. So why do we care? Why do we study microgravity? Well, obviously, we want to travel deeper into space. And in order to do that, we have to put people on a thing that moves through space at micro or close to zero gravity. So we need to find out what happens with that and how do we mitigate those problems of bone loss and things like that, muscle density, that sort of thing. Also, many things behave differently in microgravity. We need to know that, again, as we're traveling through space, but also it helps us here on the planet. So, for example, crystals grow far more perfectly in zero G than they do here on the planet. And crystals, things like proteins, create crystals as well. So we're not talking about just the geode-looking candy crystals that we grew at Christmas every year. So as we're doing research on things like DNA forms crystals, and they form more perfect crystals in space, and so we can actually do research on things like Parkinson's disease in space that we can't do as well here on the planet. Let's talk just for a moment about mass versus weight. That's something we're going to hear a lot about. And so weight is something completely different than mass, though they're related concepts. And I actually am going to let astronauts do this because they will do it far better than I ever could, and they can do it in space, which makes everything far cooler. So before I get to that, though, let's talk a little bit about a fella. His name is Sir Isaac Newton. He came up with laws of motion. 3 of those laws they're all going to come into play here as we talk about mass and microgravity and things like that. So let's really quickly, just a refresher, what those 3 laws are. The first one, an object will stay in motion unless acted upon by some outside force. The second one is the force equals mass times acceleration. So the larger mass something has, the more force you need to move it, and that's true even in space. And then, of course, the last one, for every action, there's an equal and opposite reaction. We all know these. I just wanted a quick refresher before we move forward. So let me turn it over to the astronauts on the International Space Station to tell you about the difference between mass and weight.
Hi everyone, my name is Nicole Stott and I'm a flight engineer with Expedition 20 on the International Space Station. And we're here today with you on the International Space Station and the Japanese Laboratory Module.
Hi, I'm Bob Thirsk. I'm also a flight engineer aboard Expedition 20. The topic for today is weight versus mass, a heavy-duty concept.
So what is weight? Weight is the vertical force exerted by a mass as a result of gravity. Weight also means the strength of the gravitational pull on the object. That is, how heavy is it? Weight is dependent on gravity.
On Earth, in a 1G environment, an astronaut in his spacesuit would weigh 360 pounds. On the Moon, in 1/6 Earth's gravity, the astronaut would weigh 60 pounds. In orbit, he would weigh 0 pounds because weight is dependent on gravity and the effect of Earth's gravity is not observed.
Using more physics and mathematical terms, weight is defined as the force with which a body is attracted to Earth or another celestial body, equal to the product of the object's mass and the acceleration of gravity. So in equation form, gravity equals mass times acceleration due to gravity. On Earth, that's 9.8 meters per second squared.
But what is mass? Mass is the property of a body that causes it to have weight in a gravitational field. The mass of an object is not dependent on gravity. Mass is the amount of matter in an object. Bodies with greater mass are accelerated less by the same force.
If we use the same force on these two animals, the elephant, which has a greater mass, is affected less than the mouse, which has much less mass.
And what is gravity? Gravity is a force that governs motion throughout the universe. It holds us to the ground. It keeps the moon and the station in orbit around the Earth, and the Earth in orbit around the sun. It is best described as the attraction between any two masses, most apparent when one mass is very large, like the Earth. The acceleration of an object toward the ground caused by gravity alone near the surface of the Earth is called normal gravity, or 1G. This acceleration is equal to 9.8 meters per second squared, or 32.2 feet per second squared. If you drop an apple on Earth, it falls at 1G. If an astronaut on the space station drops an apple, it falls too. It just doesn't look like it's falling. That's because they're all falling together. The apple, or the onion, the astronaut, and the space station, all falling together.
Well, what is microgravity? The International Space Station and us astronauts aboard are traveling at approximately 28,000 kilometers per hour, or 17,500 miles per hour. And we're essentially falling around the Earth, creating weightlessness. The weightlessness that is felt in free fall on a ride at an amusement park or on the International Space Station when it circles around the Earth is microgravity. Objects in a state of free fall in orbit are said to be weightless. The object's mass is the same, but their weight would register 0 on a scale. Weight varies depending on if you're on Earth, the Moon, or in orbit, but your mass always stays the same. First thing that Koichi and I would like to do is demonstrate that we're actually on board the International Space Station and we're in a weightless environment. So let us show you a few little tricks here that will make that point. I'd like to have an arm wrestle with Koichi. Let's see what happens.
This is great, actually. Okay. Then smaller.
One of my favorite Japanese sports is sumo wrestling. We're going to try to sumo wrestle.
the somersault.
Okay, Nicole, show us your stuff. Where'd she go? Come back. It's Superwoman.
So I think they explained that far better than I ever could, because I can't, do somersaults in the best of times. Just a quick recap. If you look at one of the things they showed you, which was the difference between pushing the elephant and the mouse on Earth, that same force that didn't even move the elephant shot that poor little mouse across the screen because of the greater mass. Now what happens in space? Sort of the same thing. So the elephant moved a little bit, but it's still because the mass didn't change. So it still takes greater force, even though they're in microgravity. If you drop a ball on Earth, what will happen? Well, it falls to the ground, obviously, at 9.8 meters per second per second. But in space, on the International Space Station, falling in conjunction with the International Space Station at 17,500 miles an hour, it pretty much just stays where it is. So if you were doing mass versus gravity experiments in your classroom, you can see how you could use these different experiments. We used to do things, we'd put different people in the rolling chair and push them across the room and see who took the most force and things like that. There's a really great exercise that you can do. It's mass versus weight. It's called air-powered mass. It's a great classroom activity. You can find that on nasa.gov. If you just put in the search engine air-powered mass or mass versus weight, it will show up. You use the same basic tool that you would if you're blowing the end of a wrapper off your little brother or sister. Not that any of us have ever done that at the table. Let me show you a quick demonstration they do on the International Space Station using air-powered mass to give you an example.
Bob now has a water container, which is an empty container. And also we have a air gun, and from this cylinder there's a air exit here, and Bob can squeeze the air out of this, and we will demonstrate how this water container will move with the force of the air. Okay, as you saw, with the empty or the filled with air, this drink bag moved pretty quickly. And now we have another bag which is filled with water and looks like the same, but inside it's filled with water. So the mass is different. Now we will demonstrate the same thing with this water bag. And as you can see, with the higher mass, this bag did not move as quickly as the other bag with the air. We'll do that again. Okay, so that was the demonstration, and you saw the difference between the air-filled bag and a water-filled bag. Since masses are different, you saw the difference in the acceleration as a result from the same force applied to the bags.
So I have to say that astronaut Bob has the most soothing voice I've ever heard. I want him to be my kindergarten teacher. He was awesome. So to wrap up, I'm going to leave you with your assignment. Your assignment is to go to the nasa.gov microgravity website. There are a lot of great resources for you on there. I want you to look at one in particular. There's a game called Free Fall Ball. I want you to play the game. You will be shooting a basketball in both microgravity and regular gravity. Then I want you to work with your students, perhaps, and talk about if you were going to code a game for your design, the design of your sled that you're going to bring and work here, how would you code that differently than the free fall basketball game on the site now? So using your design, how would you code that? How would that work? What would that look like? Going to write that up and then post that on the badging site, and that will wrap us up for PD number 2.